discussing cases where the Schrodinger equation can be solved exactly. We discussed a particle in a box, we discussed the harmonic oscillator, we discussed the hydrogen atom, and now very quickly I have told you the results for the rigid rotator. Now, so therefore, you may be under the impression that the Schrodinger equation can be solved for any problem, but that is not the way it is. In fact, there are only very few problems for which you can find analytic solutions of the Schrodinger equation. These days, of course, you have very powerful computers, and therefore, you can actually solve the Schrodinger equation numerically on the computer, right. But suppose you do not want to do that, because you see numerical solutions many a times do not give you physical ideas. Physical concepts are not very transparent if you have a numerical solution. So, and also there are problems in which you are not terribly interested in finding the exact solution. You would be happy if you can get some kind of estimates and understand the phenomenon. So, there have been approximate procedures of analyzing the solutions of the Schrodinger equation. I mean, for example, imagine that I have a diatomic molecule like the one that I was describing to you now, and what I am going to do is I am going to subject it to an electric field. Right. The molecule was freely rotating, but the moment I say okay, I will subject it to an electric field in maybe in the z direction, then what happens is that the space is no longer isotropic. Earlier it was rotating freely, but the moment you say there is an electric field acting in the upward direction, what will happen? The molecule, you see, molecule has usually molecules have dipole moments, right, which means that one end is positively charged and the other end is negatively charged. So, if the molecule has a dipole moment, what will happen? You see, the electric field will interact with the dipole, and so the rotation will no longer be completely free, right. So, therefore, you are externally acting on the molecule essentially. If the moment I switch on an electric field, I am affecting the motion of the molecule, right. And so, what will happen is that the Schrodinger equation that I would have will no longer be the simple one, it will have an additional term coming from the interaction of the molecule with the externally applied electric field. Okay. And many a times this external influence that you make on the molecule, it is not large, it is only a small disturbance, right. And therefore, I can give you other examples. See, suppose I talked about a conjugated system, maybe something like this. There are hydrogen atoms, I am not showing them. Okay. There are hydrogen atoms as many as you want to satisfy the valencies of these carbon atoms. And then the simplest thing is to say okay, I would have a particle in a one dimensional box which looks probably like that, right. And I would say okay, if I am interested in the pi electrons of the system, they may be assumed to be contained in a box of appropriate length, and they cannot go outside, and then you will calculate the allowed energy levels of such a system, right. This is something that I have already told you, but now suppose I have, as a chemist, you see, I can always replace this one of the carbons with a nitrogen, and suppose I want to think of this system. What is happening is that, well, you can say, at least roughly speaking, the potential is the same in these regions, but when it approaches the nitrogen, nitrogen is more electronegative, and therefore, in that region maybe the potential energy is not the same as elsewhere, but it is going to be less. So, therefore, if I had such a molecule, what will I do? I will say okay, the box is not exactly like the one previously, but what it would have is in the vicinity of the nitrogen, the potential is lower, which I can perhaps draw in this fashion. So, you see, if it is in this region, I say the potential is lower, while if it is outside, the potential is the same as before. This is a very crude model, admittedly, but then you can say what is happening is that there is a slight modification of the potential in a small region, and that what will it do? You see, originally if you were thinking of this system, the ground state, the lowest possible state would look something like that, you know that, because we have discussed this. And then what the question that I would ask is, suppose you make this slight change in the potential, what will happen to the wave function? How much would it get modified? Not only how much would it get modified, how much would its energy change? You know definitely that the energy of the system has to change. So, how much would it change? And this is only a small disturbance, right. Now, I can also give you another example. Imagine that I have a hydrogen atom. So, here is my hydrogen atom, and you know that the electron may be sitting in the 1s, if the hydrogen atom is in the ground state, or maybe it may be sitting in 2s or 2p, whichever state you want. Okay. And well, let me just depend upon your previous knowledge. You have to give an energy of 13.2 electron volts if you want to remove the electron from the ground state of the hydrogen atom. 13.2 electron volts are required. That means if you wanted to remove the electron, roughly speaking, from here to maybe 10 angstroms away, you have to supply roughly, I mean this is only rough, because strictly speaking this is the energy required to take it to infinity, but I mean once it is 10 angstroms away, the influence of the proton is negligible. Okay. So, roughly if you have to take it to a distance of 10 angstroms, you have to spend that much energy. And this means, I mean this is only a kind of estimate that a physicist would make. This means that approximately speaking, you have an electric field that the electron is experiencing. You see, the proton is charged, and therefore what will happen, anything around it will feel an electric field, and I want to know how much is the magnitude of the electric field. So, from this information typically I can calculate the electric field. What I would find is that it will be something like 13.2 divided by 10 angstroms is how much? 10 into 10 to the power of minus 10 centimeters, 10 meters, correct. So, approximately what will happen is that, well, electric field, of course, I mean I should say 13.2 volts divided by that, and therefore what happens is that you will estimate, roughly speaking, there should be something of the order of 10 to the power of volts per meter. The electric field, I mean this is a very crude estimate to give you an idea. The electron near the proton actually feels an electric field of the order of roughly 10 to the power of 10 volts per meter. Now, suppose in my lab I am doing an experiment in which I apply an electric field. The electric field that I apply may be 100 volts over a large distance, not a small distance of the order of angstroms, right. So, the electric fields that we normally apply, but of course I can have specialized experiments where the electric fields are very large, but normally the electric fields that we would apply would be very small in comparison with the electric field that the electron experiences within the atom. So, therefore, if you are thinking of the hydrogen atom, you can say, okay, I have my Hamiltonian for the hydrogen atom. I am not going to write down the Hamiltonian, but you know what the Hamiltonian is for the internal motion of the hydrogen atom. And if you say that you are going to apply an external electric field, which you may denote by, well, what notation should I use is a question. Well, let me denote it by capital E, and if you apply it in the z direction, what will happen is that there is an additional term because of the interaction of the electric field with the charges, and that additional term would look like this, minus E into capital E. Capital E is the externally applied electric field, and z is the z coordinate of the electron. Why z coordinate? Because I am applying the electric field in the z direction. If you had applied it in the y direction, then you would have had y there. So, effectively, I mean The details are not very important at this point of time. The effectively what is happening is that I have a Hamiltonian, right, like maybe the harmonic oscillator or the hydrogen atom. What I am doing is I am modifying that Hamiltonian by a small amount, changing the Hamiltonian by a tiny amount by applying an external electric field or by replacing one of the carbons with a nitrogen. Again I am modifying my potential there. So, I can now generalize this and say, okay, I have a Hamiltonian which I will denote as H0. Now, this notation can be confusing because this may mean h to the power of 0. I mean, you may interpret this as h to the power of 0. I do not want that to happen. So, I will put this 0 within a bracket to indicate that this is my Hamiltonian. For example, this may be the Hamiltonian for the hydrogen atom without any electric field, or it may be the Hamiltonian for the harmonic oscillator, one of these things for which we actually know the solution of the Schrodinger equation, or maybe for the rigid rotator, we know precisely, today we have seen the Hamiltonian. So, it is one of them. And then what am I going to do? I am going to have a perturbation. Perturbation means disturbance, right. How you apply maybe an electric field or something you do, right, to replace a carbon with a nitrogen. So, therefore, I have a disturbance, and that disturbance I am going to write as lambda times H1. Why did I introduce a lambda? Well, if you want to have a physical example, you can think of lambda as the electric field. If you feel like it is not necessary to think of it as the electric field. So, there is a parameter lambda, maybe the electric field. When I change the value of lambda, what will happen? The disturbance that I cause is going to change. I mean, I increase the electric field, so the disturbance will increase. So, and this is my total Hamiltonian of the system. Okay. Well, maybe I should put hat everywhere, and this actually is a h is now a function formally of lambda. But as I have told you, the effect of this term I would expect will be small in comparison with the effect of that. This is huge. I mean, for example, hydrogen atom example I have showed you, electric fields that exist in the hydrogen atom could be of the order of 10 to the power of 10 volts per meter, while the electric fields that I apply may be perhaps 100 volts per meter, or much smaller essentially. So, what is it that I want to do? I want to find solutions of this equation h lambda operating upon psi is equal to E psi. But because your h is dependent upon the parameter lambda, what would you expect? The energy also has to depend upon the value of lambda. I mean, if I have an electric field applied, then naturally the energy of the system will change when I change the electric field. So, therefore, this has to be a function of lambda. Not only that, the wave function, when I change the electric field, the wave function also should change. Therefore, this is going to be everything is going to depend upon lambda. That is actually obvious. And further, you see the way things are, I know exactly the solution of the Schrodinger equation for this Hamiltonian, because you see this is, for example, the hydrogen atom. I know precisely what the solutions of the Schrodinger equation are, correct. Our Hamiltonian is such that I know, I am assuming that I know the solutions of the Schrodinger equation if this was the Hamiltonian. That means, if lambda was equal to 0, suppose lambda was equal to 0, then my Hamiltonian will be that, and I know what the solutions are. So, therefore, let me say that imagine H0 operates upon something, I will need a notation for that, that will be equal to some E into psi, correct. Well, here effectively what is happening is that I put lambda equal to 0, right. and then what will happen here, I would have psi when lambda is actually equal to psi when lambda is equal to 0, and how many psi's can I find? I can solve this exactly, therefore, I would have found all possible solutions. So, a large number of in principle infinite number of eigen functions and eigen values. So, therefore, I would have different possible states of the system which I may denote with the subscript n, and here also I would have to put the subscript n, here also I would have to put the subscript n, because the energy will depend upon that subscript, right. And then what will happen is that you see these are actually eigen functions of your unperturbed Hamiltonian. And this term, so this H0 is referred to as the unperturbed Hamiltonian, while this one is referred to as the perturbation. This whole thing is my perturbation, that is how I disturb my system. And when you look at this equation, you see the psi n's here are eigenfunctions of H0, the unperturbed Hamiltonian. So, therefore, because we are going to have several psi's sitting in different places, it is best that I put a superscript 0 here also, because these are solutions corresponding to that Hamiltonian, which means that I should put a 0 here or here as well as a 0 there. It is necessary, so that we should not get confused when I look when we say different psi's. So, the moment you see this 0 there, you will realize that this is actually an eigenfunction of H0. Okay. And further this psi n 0, well one more thing I want to say, your unperturbed system had several energy levels, correct. So, if I can draw the allowed energy levels, this is probably something like the allowed energy levels which are having energy En 0. You can have the ground state with n equal to 1, next state with n equal to 2, or ground state with, I should not say n equal to 1, n equal to 0 is the usual notation for the ground state. And then what will happen as I increase my electric field, or as I increase my disturbance, what will happen is that these energy levels are going to change. So, therefore, let me say what is going to happen is that I will have a new ground state, then another new first excited state, another new second excited state, third, fourth, etc. So, the energy levels are no longer coinciding with this. So, this is the ground state, this one is the ground state in the absence of any disturbance, and this is the first excited state in the absence of any disturbance, first excited state with the disturbance, and so on. So, therefore, you see this Hamiltonian itself has several different eigenfunctions and their corresponding eigenvalues. So, it is only natural that I should put a subscript n here, a subscript n here, and a subscript n there. And further, I actually know that E n lambda as I change the value of lambda, what will happen? E n lambda is going to change, correct. And if I had lambda very small, lambda close to 0, what will happen? E n lambda will actually be equal to the unperturbed energy level, and therefore, I would say that E n 0 will be, if lambda is 0, this is actually true, but if lambda is not true, sorry, lambda is not 0, then this will not be true. But if lambda is very small, then what I can say is, okay, there will be corrections to this energy, and those corrections will be, well, you can say linear. The small corrections that you would have will be linearly dependent upon lambda. So, therefore, I would have to say okay lambda times the correction, right, it will be linear, but now you can imagine that when lambda is very small, this E n is a function of lambda. So, you can imagine that you are going to do a Taylor expansion of E n lambda about lambda equal to 0. If you did a Taylor expansion, what will happen? You will get I mean maybe if you want I can remind you f of lambda. If you did a Taylor expansion, what is going to happen? You will get f at lambda equal to 0 plus lambda times f prime at 0 plus lambda square by 2 factorial f double prime 0 plus etc. That is what is going to happen. So, what is important for us is actually it is possible for me to imagine expanding E n lambda as a series in lambda, and the first term, the unperturbed term will be E n 0 and the next term will be lambda times E n 1. I will this is my notation, this whole thing is my correction to the energy, and then if I wanted the next correction, what will happen is that it is going to be equal to lambda square into E n 2 plus etc. So, that is the way I write the expression, and now I will use the following words. This is my unperturbed energy, this is my first order correction to the energy, that is my second order correction, then I can think of third order, fourth order, fifth order, okay, if I want. In a similar fashion, I can think of the wave function. What will happen with my wave function psi n lambda? I can imagine what is going to happen is that I would have psi n 0 plus lambda times psi n 1. This is actually this whole thing is my first order correction to the wave function, then lambda square times psi n 2 second order, this whole thing again is my second order correction to the wave function, and so on. So, what is it that I would like to do? I would like to estimate the first order correction to the energy. I have applied an electric field and I want to know what is the modification of the energy level. So, this I would like to calculate, if possible I would like to calculate that, and so on. But I already, as I told you, the disturbance is usually small. So, maybe it is enough if I just calculated the first term, because I would expect that the second term will not be that much important, because you look at this, it involves lambda square. Suppose lambda was identified with the electric field, and the electric field, as I said, is very small in comparison with the electric field that exists in the atom. So, therefore, this is a term that is linear in the electric field, this will be a term that will be second order square of the electric field. So, you would expect that this correction to the energy will be much smaller than this correction, unless of course you have a large electric field, right. So, therefore, we would be happy if we can estimate this and perhaps that. In fact, you can derive expressions for those also, but we will not go into those expressions, right. So, what am I going to do? I want to determine these things, and of course, you see what do I have? I have the Schrodinger equation. This is the Schrodinger equation that I have. Of course, this is the time independent Schrodinger equation. So, let me write that equation once more. I know that h lambda is given by this expression. So, therefore, I am going to say I would have h 0 plus lambda times h 1 operating upon psi n where is psi n? Psi n is sitting here. Well, psi n lambda I am going to write as psi n 0 plus lambda times psi n 1 plus etc. is equal to So, this is what happens to the equation. Now, even though you would not have realized it, I have made a very strong assumption in whatever I have done. Let me tell you what that assumption is. This says that if I put lambda is equal to 0, my perturbed wave function actually will become equal to psi n 0, that is what it assumes. This is true in general, provided your energy level is non-degenerate. Okay. If your energy level is degenerate, let us say it is doubly degenerate, then when lambda is equal to 0, you see, I mean, I do not have a unique state, because there are two states there, right. So, what would this be? Can I think of a unique state, or maybe it can be a linear combination of the two states that are already there. It may be it may be the first state, it may be the second state, or perhaps it may be a combination of the two, I do not know. So, this expansion actually assumes that I know uniquely what this psi n 0 is, and that I can do only if my energy level is non-degenerate. And therefore, whatever I am actually developing is applicable only for non-degenerate levels, it is not applicable for degenerate levels. Actually, strictly speaking, I should make a discussion of degenerate levels, but I am not planning to do that, because we will discuss the other method, which is referred to as the variation method, and it is fairly straightforward to make use of that method even for cases where you have degeneracy, there is absolutely no problem. So, whatever I am doing is valid for a non-degenerate level. This actually means that if you are thinking of the harmonic oscillator, then things are fine, because for the harmonic oscillator everything is non-degenerate. If you think of the particle in a box, also everything is fine, because they are all the allowed energy levels of the particle in a box are non-degenerate. But if you think of the hydrogen atom, then you have to be careful. The theory that I am developing, it will be definitely applicable for the ground state, because ground state is non-degenerate, it is the 1s state. But it will not, if you are going to apply, if you want to apply perturbation theory to the other states, then you have to be careful. Okay. Now what I want to do is, so therefore I have already told you that this equation is constrained in that psi n, or this energy level E n 0 is assumed to have only one state, it is non-degenerate. Now what I am going to do is, you see, I know that this equation the left hand side should be equal to the right hand side for any value of lambda. You have, if you look at this, you have a power series in lambda. Actually, you can say, okay, remove this equal sign and make it negative, and then what will happen? This has to be equal to 0. So, if you look at this, it is a power series in lambda, and the power series has to be identically equal to 0 for all values of lambda, starting from 0 to some value. And if that is to happen, what is the condition? We already know what the condition is. You can think of it as a power series in lambda. The coefficient of each power of lambda should be equal to 0. So, let us do that. The other thing that you should remember is that these are all, there are operators. So, therefore, I have forgotten to put the hat sign. So, better that I put the hat sign. So, what is the coefficient of lambda to the power of 0? From here you are going to get right, this into that is going to be giving me a term that does not depend upon lambda. So, H0 operating upon psi n 0 is one term, and from here you see this is occurring with the negative sign, because I should not forget the negative sign, let me put it here. So, this into that is going to give me a term that is independent of lambda. So, therefore, the first term will be h 0 psi n 0 minus E n 0 psi n 0. This is the coefficient of lambda to the power of 0, the term independent of lambda, and then I would have a term that is linear in lambda. What is that? H 0 operating upon this one. Remember, lambda has no position dependence, lambda is like your electric field, which is the same everywhere. So, therefore, H 0 operating upon lambda, lambda is unaffected, right. It is just a number, so it is unaffected by H 0. So, what you are going to get is H 0 operating upon psi n 1. Is that all? No, because there is a lambda here, that lambda has an H 1 and that can go and operate upon psi n 0. So, this lambda is there, and I have already taken into account of lambda because I put a lambda outside. Minus, what will happen? You will have E n 0 multiplying that. And then you will have this term multiplying that. So, that is going to be minus E n 1 psi n 0. I will continue in my next lecture. What I shall do then is to write the term that depends upon lambda square, and then you will have lambda cube, etc. The series actually continues, and everything together is equal to 0. But because this is a power series in lambda which is identically equal to 0, what will happen is that the coefficient of each power of lambda must be 0. So, therefore, I will have many equations to work with. So, we have this power series and we say that the power series has to be equal to 0. I will just fill in the coefficient of lambda square . It is not actually very difficult to write it down, because you see, if you look at the one that corresponds to lambda, if you look at this coefficient, you will see that the sum of this 0 and that 1. If you just added these two up, answer is 1. If you added these two, answer is 1. Those two are 1, add those two 1. So, naturally, if you had lambda square, what you would expect is that if you added those things, you should get 2, that is all. So, that remembering that, you can easily write down. So, H 0 is I n 2 plus H 1 psi n 1. There is no H 2, that you have to remember. H with the superscript 2 is not there, because this is the perturbation. Minus E n 0 psi n 2 minus E n 1 psi n 1 minus E n 2 psi n 0. This will be the coefficient of lambda square. Similarly, if you wanted to write the coefficient of lambda to the power of 3 or 4, it is not difficult, easily you can write it. But anyway, we are not going to be worried about the higher terms involving lambda square or lambda cube. We will only be interested in these two equations. Why? Because I am interested in first order correction to energy and first order correction to the wave function, right. So, let us look at these two equations. What do they tell us? It tells me that this must be equal to 0, that is the first thing. So, what is that equation? The equation says that H 0 psi n 0 must be equal to E n 0 psi n 0, but this we already know. I mean, this equation is satisfied, because this is just the unperturbed Schrodinger equation corresponding to the unperturbed Hamiltonian. So, nothing new, this we already know. Well, if you look at the second equation, what is the second equation? It is the coefficient of lambda. What are you going to get? You are going to get h 0 psi n 1 plus h 1 psi n 0 minus E n 0 this is what the equation says. Right. I hope I have not made any mistakes on the superscripts. Now, among in this equation what is going to happen is that I actually know what psi n 0 is. Psi n 0 is I know because I have solved the Schrodinger equation for the unperturbed problem. I also know what are the other things that I know. I know this one, I know this term, yeah, that's all that I know, right? But I do not know E n 1. So, what I will do is I will take the terms that involves psi n 0 to the right hand side. So, I would have h 0 psi n 1 minus E n 0 psi n 1 is equal to something. What is that something? Well, please check this. What have I done? I have retained this term as well as that term on the left hand side and removed the other terms and put them on the right hand side. Correct? Now, I want to find out E n 1, for example. Now, it seems difficult, but actually it is very easy with this equation. All that you need to do is you multiply from the left hand side with the psi n 0 star. This is known to us, psi n 0 is known to us. So, therefore, I can multiply throughout by psi n 0 star maybe I will write the terms separately, psi n 1 d 2 that will be the first term minus E n 1 sorry not E n 1, but E n 0. Remember E n 0 is a constant, so it is unaffected by the integral sign. So, you will get integral d 2 psi n 0 psi n 1 with a star here. That will be the second term. What happens to the right hand side? I would have E n 1 integral psi n 0 star psi n 0 d 2 minus integral d 2 psi n 0 star h 1 psi n 0. It does look messy, but it is actually fairly simple to evaluate this, because I know that this term, how much is this term? See, these are functions, eigenfunctions, they are all, oh no, that I do not know. This is the one that I was talking about. This object I know. Psi n 0 multiplied by psi n 0 star integrated over the entire space, answer is unity, because the function is normalized. So, let me just remove that. So, this is actually unity, this whole thing is equal to unity. And now, if you look at this expression, what is it that I have? I am going to look at this expression. Where do I write? Maybe I can remove these things. The integral that I have is integral d2 psi n0 star h0 psi n1. This is the object that I have. But I know that H0 is a Hermitian operator. So, I can make use of the properties of the Hermitian operator. So, how will I make use of the properties of a Hermitian operator? It is actually equal to in d2, you can allow H0 to operate upon psi n0 instead of it operating upon psi n1. Okay. And you can put psi n1 star on the other side. And from the properties of the Hermitian operator, I know that these two have to be complex conjugates. So, therefore, properties of the Hermitian operator imply that this has to be valid. And that is actually very nice, because see here H0 was operating upon psi n1, but there H0 is operating upon psi n0, and this is an eigenfunction of H0. So, what will be the answer? You will have integral d2 psi n1 star E n0 will be the answer of this operating upon psi n0, multiplied of course by psi n0. So, that is what it is, correct. And I can take the star operation inside. What is going to happen? E n0 is an eigenvalue. Eigenvalues of Hermitian operators, they are real. So, this starring will have no effect on this. I can take it out because it is just a real constant. Then I would have integral d2, again take the star inside. So, you will have psi n1 multiplied by psi n0 star. Correct. So, we have evaluated this and found that it is equal to that. And if you look at this equation, you would realize that this we have evaluated and we have found that it is exactly equal to. Look at that and you look at this, you will see that they are the same. So, therefore, this and that are actually equal, and therefore, they will cancel each other, right. And hence, what is it that I have left with? I have left with 0 equal to E n1, right. This is actually equal to 1, this term we have said it is equal to 1 minus integral d2 psi n0 h1 psi n0 with a star, of course. Well, I will rewrite that equation, write that equation once more, so that the idea is very clear. There is a 0 here, so I will take En, I will take this to the other side. I mean, I can write it as an equality sign. So, what do I find? I find En1 is equal to how much? Integral of d2 psi n0 star h1 psi n0. Now, what is our first order correction to energy? First order correction to energy, strictly speaking, is lambda times that. So, what will happen? I will have to put that lambda back and I will get this. So, this is my first order correction to the energy. Fine. Now, what does it say? You look at the physical content. Whenever you have an equation, you should be looking at the physical content and understanding that. What it says is, here is your perturbation. And what is it that you have here? The unperturbed eigenfunctions. right. So, if you wanted to calculate the first order correction to the energy of the nth state, what you should do is you should take the perturbing Hamiltonian, calculate its expectation value using the unperturbed wave function, that is all, very simple. You know the unperturbed wave function, you know what the perturbation is, and therefore, you can easily calculate this, it is not difficult at all. Thank you for listening.